This video looks at giant covalent structures. So we know what covalent bonding is already. It's a bonding that takes place between non-metal atoms, and it happens by sharing a pair of electrons. And then we know that covalent compounds and elements almost always exist as molecules. So for example, you are familiar with water, which is H2O. A single molecule has one oxygen atom and two hydrogen atoms. There are a couple of exceptions that don't exist as molecules, but they exist as giant structures, a little bit like metals and ionic lattices. I'm going to go through the two main examples. The first one is diamond. Both the ones I'm going to do are made of carbon atoms. So I'm going to draw carbon atoms. I'm going to represent carbon atoms with a little circle like that. Let's just look at carbon on the periodic table. We see it's in group 4. So to get its full outer shell of 8 electrons, each carbon atom is going to be looking to get 4 more electrons. So it's going to be looking to make 4 covalent bonds. And that's what happens in diamond. So I'm going to draw the covalent bonds just with lines, and I'm going to, for this diagram, draw the atoms with circles. And then if I kept on drawing, we'd see that each carbon atom is bonded to 4 others. And you'd see also that it's not very easy to draw because we're drawing in 3D. And I'll just finish by doing that last one there. I could, of course, go on forever drawing this structure, but hopefully just drawing that tiny section of it gives you the idea that every single carbon atom is bonded to 4 others, and that this is a 3-dimensional structure. So those are the main points about diamond. I'm just going to write each C is joined to 4 others. That means each carbon atom. And this is a 3D structure. Okay, the other example that we'll look at now is graphite. Graphite bonds differently. This time for graphite, each carbon atom joins to 3 others only. And that makes graphite actually quite a lot easier to draw. So if I kept drawing them, each one being bonded to 3, we'd see pretty soon that we end up with a pattern of hexagons. It looks basically like a honeycomb. So this is a flat structure in this case. In this case, it would just form a 2D layer. And with graphite, we get these 2D layers, but then if I was to take that 2D layer and turn it the other way around, you'd actually see that there are stacks and stacks of these 2D layers. So that's how its 3-dimensional is. It's just loads and loads of layers on top of each other. So I'm going to write that in. Each C joined to 3 others. It's a 2D structure, but these 2D layers go on top of each other. So that's what we see from the other way. The other question is, if each carbon atom is joined to 3 others, what happens to that last electron? And the answer is, it becomes delocalized. That means it's free to move, no longer associated with a certain atom. And those delocalized electrons exist between the layers like that. So that's the last point to note down, delocalized electrons between the layers. Okay. So those are the two main structures. They're both forms of carbon, but they have totally different properties, and we'll look at that in a different video, how diamond is different to graphite. And we call those allotropes. That means they're the same element, but they have different physical forms. And in this case, they're different physical forms of carbon. just as a side note from a different video, there is another form of carbon which isn't diamond or graphite, and that is Buckminster fullerene, which is massive molecules, C60, so a molecule with 60 carbon atoms, and it forms this football shape of pentagons and hexagons, and that's a nanoparticle. So that is, if you like, a third allotrope of carbon, but it's not a giant structure in the same way that diamond and graphite are. And just the other one, you've got to know that diamond and graphite are giant covalent structures. There's one other that's really important to note, and that is silicon dioxide, which you might not have heard of, but silicon dioxide is what most sand is made from. So that's the reason why sand and diamond are both very hard solids. They have the same structure. So in this case, you just imagine instead of this being carbon atoms, these are alternating silicon and oxygen atoms. Those are your three that you need to remember have got a giant covalent structure.